Hi folks, my name is Arun Thiraviam and I am a Simulation Product Specialist with GoEngineer. First off, I'd like to congratulate you on investing in an analysis tool. You are now part of a group of 1 million engineers who use this tool to develop better products. What I'd like to do today is to essentially walk you through some of the capabilities that you have access to with the Simulation Standard license for structural analysis. Now, from making good products to great marketing material, you will soon reap the benefits of actually running physical tests within a virtual environment. Now, let's take a quick look at what kind of capabilities you have access to with the software. Alright, so with this license you have 4 tools. Starting with the static analysis. Utilized by R&Ds world over, this analysis helps you test products for structural strength. You get to apply the loading conditions experienced by your parts and assemblies to determine areas of structural weaknesses. Next up, the trend tracker. As the name suggests, this tool tracks trends. It helps you monitor structural performance when a change is made to the shape of your design. A report is created with the static study that compiles the history of stress, displacement, and strains for all the design iterations you've tried to essentially select the design that works best. Next up, fatigue. Now this is a high cycle fatigue analysis tool that utilizes a combination of material ascent data and cyclic loading conditions to determine the life cycle of your product. Number of cycles to structural failure and damage are typical results you get from this tool. It helps find areas that are susceptible to fracture and failure due to repeated loading. Finally, motion analysis. Now as the name suggests, this is a rigid body dynamics tool that simulates the movement of your assemblies. It takes forces and contacts as inputs and uses mates defined in the assembly to calculate the dynamic behavior of parts. Now, a popular use of this tool is to study mechanisms such as latches, cams, robotic arms, actuators, suspension system, conveyor belts, and anything that moves really. Now today I will be discussing the following topics, which should get you up and running with the tool. Now I have the time signatures listed here in case you'd like to skip to a specific topic. Now let's begin our analysis journey. We'll start by firing up SOLIDWORKS and opening a new part. Now to access the simulation tools and the associated tutorial files, we will first need to add in this module. Now this can be done from the SOLIDWORKS add-ins tab on the command manager. Now let's select the SOLIDWORKS simulation button. You will know that the module is present when the command manager updates with the simulation tab. Sometimes you'll just need to give this a second. Now the tutorial files can be accessed from the help menu. Go to help, SOLIDWORKS simulation, and tutorials. Now this should bring up a window to the right side of the screen. Now these files are segregated into the different simulation tiers. For now, we'll just be focusing on the files under the SOLIDWORKS Premium and the Simulation Standard tabs. Now, under the SOLIDWORKS Premium tab, let us select the analysis of a part item. And here is our problem description. Now, we have a bracket made of alloy steel that is subjected to a pressure of about 250 psi. Now, the goal of this exercise is to determine if the bracket fails at this condition, and also to understand the steps taken to set up an FEA problem. Now you can advance through the steps of the tutorial by clicking the button on the bottom right corner of this window. In the first page, you will find a link that lets you open the file in SOLIDWORKS. Now let's hit yes on the security warning and proceed. Now I'm pretty familiar with the setup, so I'm closing this window out, but you could always go through the steps and use this as a reference for this analysis at a later time. Now let's set up our first analysis. Now grab the new study button from the simulation tab and select the static button. Now rename the study and hit the green check mark. You will notice that the feature manager window updates to have the analysis tree. You will be able to apply materials, loading conditions, and generally set up the analysis here. Also notice the analysis tab created at the bottom of the window. Let's start with the material properties. Now right-click the Tutor 1 item, which is the part name, and hit the Apply Edit Material item. Now this should bring the material database window in the software. Here you have a whole host of metals and non-metals to pick from. Now all the standard materials are in the white folders, while you can create custom materials in the blue folder. For this analysis, we will use the standard alloy steel material. Note that the properties highlighted in red are necessary to run this analysis. So if you're creating a custom material, you will need this information. We'll get into what these properties mean a little later. Now, as this is just a part analysis, you can ignore the connections item for now. Next, let's apply a fixture or constraint. Right-click the fixtures item and select any item from the tree. This should open up the fixture manager. Now there are a set of standard fixtures that will be used for a majority of our applications, but you have access to some advanced constraints as well. Now select the fixed geometry item and apply this to the two cylindrical faces on the bracket. Now this completely constrains the model. Next, apply a pressure of about 250 psi in the same fashion. Right-click the external loads item and select the pressure option. Notice the other loading types as well. That will come in handy for different applications. Now select the flat face of the cylinder, change the unit system to English units, and key in about 250 psi. Finally, the mesh. Now meshing is a method of breaking down the geometry into little elements. Now this helps the solver to process the loading conditions and the stiffness of the component and evaluate the stress distribution of the part. Now in SOLIDWORKS, the default element type is a second order 3-dimensional tetrahedron. Right-click the mesh item and select the Create Mesh button. Now you can use the mesh density slider to control the size of the elements. Now the finer the elements, the longer the analysis, but the more accurate the results are. The coarser the elements, the quicker the analysis at the expense of accuracy. Now it is recommended to use the default settings that can be restored by selecting the Reset button. Now selecting the Mesh Parameters item opens up the Mesher selection. Now the recommendation is to use the curvature-based mesher, as it is able to capture a broad spectrum of complex geometry with good feature resolution. So here you will see how the density slider affects the maximum and minimum element sizes that will then be used to mesh the model. Now let's reset the slider to its default settings and hit the green check mark. Now that the setup is complete, it's time to run the analysis. This can be done by right-clicking the first item, that is, the analysis name, and selecting the Run the Study button. Once the run is complete, you will see a von Mises stress plot. Now, what is this and how do you use this to evaluate the strength of your design? Let's take a look. Now consider the simplest engineering problem you can think of, a fixed cantilever beam. Let's say we need to evaluate the strength of this beam in tension. So let's take a tensile force P on the free end. Now to determine the strength, we are going to need the cross-sectional area and the length, essentially the geometrical characteristics of the beam. Finally, we will need to know what the beam is made of. In the engineering world, we call this the elastic modulus or the Young's modulus. Now, where did this come from? Now, most engineering materials are characterized by a stress-strain curve. Now, this is generated by placing a metallic or plastic specimen in an ultimate tensile testing machine and recording its elongation or change in length versus force applied. Now stress is a measure of force applied and the strain is the percentage elongation. Hence the stress strain curve. Now a large portion of the curve is linear, meaning that in order to input this curve to the software, all you need is one number, which is the Young's modulus. Now one more thing to keep in mind is the yield point, the point beyond which metals permanently deform and fracture. Now to use this info, the stress on the beam can be estimated through force applied divided by the cross-sectional area. Now this value needs to be lower than the yield point. Now to set a standard for strength, we have the factor of safety, that is a ratio of the yield strength to the applied stress. This value is typically around 2 to ensure your designs do not fail, even if they experience twice the loads they were designed for. Now this kind of comparison is easy for beams, but in reality structures undergo many different types of stresses. So we use an equivalent stress component called the von Mises stress that takes into account all the effects of all these stresses. So to avoid structural failure, we need to ensure this von Mises stress determined by the software is less than the material yield strength. Now since the max von Mises stress is less than the yield strength of the bracket, we can state that the component is safe. Now to find out the areas that experience the most amount of stress, we can take advantage of the ISO clipping plots in the tool. Now double-clicking the displacement item on the tree gives you the amount of deflection. Now you can see the resultant or plot deflections in one of the component directions. Finally, if you'd like to compile this into a report, grab the report button from the command manager. Now this puts together all the inputs and outputs associated with the analysis in a neat Word document. Alright, in this exercise, we're going to take a look at running a simulation on an assembly. Now the setup is similar to the previous example, but involves adding connections and contacts to ensure the different components in the assembly stick together during the analysis. So I strongly recommend going through the first tutorial in this video if this is your first time using the software. Now let's fire up a new part and access the simulation tutorials from the help menu. Ensure you have the SOLIDWORKS Simulation plugin added to access these. Now under the SOLIDWORKS Premium tab, I'm going to access the bolt connectors tutorial. Alright, problem description time. Now we have a basketball rim attached to the backboard through bolts. The bolts have a preload of a certain amount. Now we're trying to test the strength of the rim, the bolts, and the board with the analysis tool. We are also going to see how we can use the simulation bolts instead of real ones to carry out the analysis. Okay, let's jump to the next page, grab the model and get started. Let's first set the unit system for the analysis. This can be done from the simulation menu and the options submenu. This should open up a window. Now select the default options tab in the window and you should have access to a few analysis settings. Now let's set the unit system for the exercise to English units. So as you get familiar with the analysis tool, you can explore what some of these other default settings do and make changes accordingly. Now my recommendation is to head over to the results item and select the under subfolder checkbox. This will compile all the metadata associated with the analysis into a results folder in the location of your part file. Now let's set up a static analysis. You'll notice the parts being analyzed are under the parts item. Let's assign an alloy steel material to all parts. As always, we're going to be right-clicking our way through the tree. Now once the materials have been assigned, let's talk connections. Now there are two fundamental types of connections or contact sets that control how components interact with one another. They are the bonded and no penetration types. Now as the name suggests, the bonded type creates a rigid bond between the contacting surfaces so the components deform together. The no penetration or sliding contact enables components to move relative to one another. If they do come in contact, a contact pressure is estimated between the surfaces. By default, SOLIDWORKS sets up a bonded contact between coincident entities. Now we can verify this by accessing the contact visualization plot from the connections item. Now hit the calculate button and you will notice the red bonded contact between the backboard and the rim. Now this set is created due to the global bonded contact entity that is automatically set up by SOLIDWORKS. So when running an assembly analysis, you will see a global bonded contact entity show up under the connections tab. Not to worry though, any user-defined contact over these surfaces will override this global definition, which is what we will do next. So let's right-click connections and select the contact set item. Ensure you have the no penetration type enabled. Select each face in the blue and pink box. Now scrolling down this menu, you will also notice a place to enter friction coefficient. Now it's time to connect these two components with bolt connectors. Now to create bolted connections between the board and the rim, you will need to select the bolt item from the connections menu. Here you can choose between different types of bolts and screws based on your application. Now you will be selecting the edges that the bolt head and the nut head sit on. in the respective boxes. The software predicts the bolt size based on these selections, but you could totally override these. Now the material property for the bolt can be from the standard library, or you can just put in your own custom properties. In this example, I'm going to use a set of values that's been defined by the tutorial. And I'm going to use the English unit system as well. Now the biggest benefit of using this feature is the ability to input a bolt preload. Let's do a 100-pound preload here. In the same fashion, let's define the other 3 bolts. Now holding down the pin lets you make multiple bolted connections at once. Now these simulation bolts are essential to the analysis process because they greatly simplify what would otherwise be a very complex analysis using real bolts. Now here, a combination of these bolts and the no penetration contact ensure that the bolts endure much of the applied load without being grounded by the bonded contact, like they would in reality. Now if you'd like to learn more about the inner workings of these bolted connections, you should check out our knowledge base or the SOLIDWORKS help manual. Next, we will ground the model by applying a fixed constraint to the split face on the backboard. Because remember, we need to somehow completely constrain the model so that a force applied leads to only the deflection of the model and the model is not allowed to move in any specific direction. Now for the external loads. Let's apply a force on the split surface at the tip of the rim. Right-click External Loads and select Force. Now if the rim face isn't in the blue box, just select it from the screen. Now we will have to define the force in the global Y direction. In order to do this, grab the Selected Direction button. Select the pink reference box and grab the front plane from the assembly tree in the UI. Now on doing so, you will be able to define the force in the component directions. Now select the second icon here to define the force in the Y direction. Let's throw in a value of about 250 pounds and ensure the force is pointed downwards. Finally, we will mesh the analysis. Right-click the mesh item on the tree and hit the Create Mesh button. Ensure the Mesh Parameters button is checked and select the curvature-based mesher. Now run the analysis by right-clicking the name of the study and selecting the Run button. Once the run is complete, you will notice that the stresses are well below the yield strength of the material and are concentrated in a very few areas. So overall, this design is safe. Now if you'd like to study the stress of an individual component, you can do so by editing the definition of the stress plot. Here, you expand the Advanced Options tab and select the Show Plot on Selected Entities button. Next, select the solid icon and grab the rim off the screen. To ensure the scale pertains to the component on the screen, go to the Chart Options tab and select the Show Min-Max Range for Shown Parts Only item. I'll turn on the annotations while I'm at it. Now hit the green check mark and here it is, the plots just on the rim. Lastly, let's check out the forces endured by the bolts. This can be done by right-clicking the results item and grabbing the list connector forces. Here you will see the axial, shear, and torsional forces experienced by these bolts that can then be used to size them. You will notice that the bolts on the bottom row endure a much higher load than the ones on the top row, as you would expect. Much like the previous example, you can also hit the report button and generate a report for this analysis to facilitate easy documentation. In this exercise, we're going to look at how to use the trend tracker tool to determine the best version of a certain design. So let's get started. Now make sure you have the simulation module added in, and we can get the next tutorial from the help menu. Now the trend tracker tutorial is under the simulation standard tab. So browse over and grab the trend tracker icon. Problem description. We have a bracket and we're going to change the dimension of this bracket to monitor how it affects the strength. In this process, we will learn how to turn on the trend tracker and pick the best design iteration with it. Now let's go to the next page and open the model. Once the model is open, you will notice a simulation study is already set up. So let's use that. Now the bracket is made of an alloy steel material. There are fixed constraints on the holes and a 1000 psi load is applied to the bracket face. All we need to do is mesh and run this analysis. As always, the run button can be accessed from the first item on the tree. Now that we have generated the stresses, strains, and displacements for the bracket, let's add the trend tracker tool and set this specific design as the baseline. This can be done by right-clicking the first item, which is the study name, and selecting the trend tracker button. This creates a trend tracker item on the simulation tree. This is how we will monitor the design. Now right-click the trend tracker item and select Set Baseline. This will set the current design as the baseline, and let's hit yes at this window. Now this is just the software warning you that the current design iteration will be saved to the file. Now JPEGs of the displacement and stress plots are generated and show up in the Windows picture viewer. Now you can close these windows as this information will be recorded in the trend journal. Now if you expand the trend tracker item, you will see a record of the mass, stress, and displacement for the current design in the forms of graphs. Now double click any one of these items to open the graph. Now you're not limited to tracking just this data. If you'd like to see how a specific simulation performance parameter changes with the changes in the design, you can do so by adding a sensor for the analysis. Now click the Evaluate tab on the Command Manager and select the Sensor button. Now switch the sensor type to Simulation Data. For this example, let's track the first principal stress. This is another component that designers and engineers use to evaluate the strength of components. As soon as a sensor is created, it shows up as the last item in the sensor folder on the Feature Manager tree. Now scroll all the way down to check out the newly created sensor. It should be called stress 2 or 3 depending on the number of times you've run through this exercise. Now time to add this sensor to the set of tracked parameters. Now right click the trend tracker item and select the Add Tracked Data Graph. Here you will see the list of all the sensors that were created for this file. Now select the last item from the list. Now expanding the trend tracker item should reveal the newly added sensor. Now let's make a change to the model. Now hit the Model tab and select a rib on the bracket. This should bring up the dimensions. Well, if you don't see them, make sure you have the Instant 3D button active. You will find this under the Features tab. Now select the dimension corresponding to the rib thickness and go from 8 mm to 10 mm. But make sure you hit the traffic light to rebuild the model with the new dimension. Now jump back into the Ready Simulation tab. It is always important to remesh the model anytime a change is made to the design. So let's hit the Mesh and Run button to update the mesh and solve the analysis. Once the solution is complete with the new design, the Save Model warning box should pop up. Say yes here to record the iteration and then close out the JPEG previews. Now let's investigate the mass graph under the trend tracker item. You will see that the change in mass due to the dimension change has been recorded. So let's open up the stress 3 graph. You will see that although we have a change in mass, we have reduced the overall stress in the model. Now repeat this process a couple of times with different rib thicknesses, say 12 mm and 16 mm. Finally, after this process is complete, you will be able to open the mass and stress graphs simultaneously. You will notice that beyond a certain iteration, increasing the rib thickness causes the load path to increase the stress in a different location. In my case, it's iteration 3. So if you like to update the model with the dimensional parameters in iteration 3, you can do so by right-clicking the Trend Tracker item and selecting the Restore Model to Iteration button. With the window that pops up, you can now select any one of the previous iterations that you believe is the most optimum solution. Now select Yes in the warning dialog box to restore the model. It is recommended that you remesh and solve the model to update the results with the design change you decided on. If you'd like to start over, you can delete the Trend Tracker from the first tree item. Now in this final exercise, we're going to take a look at running a motion analysis in SOLIDWORKS. Motion analysis is a method you can use to simulate mechanisms with rigid bodies. Let's get started. Now as always, let's ensure we have the SOLIDWORKS Simulation button added in to access the tutorial set. Now from the Help menu, browse to SOLIDWORKS Simulation and Tutorials. In the window that pops up, choose the first SOLIDWORKS motion tutorial. Prompt description. We have a spring-loaded valve actuated by a cam. We are going to figure out the spring stiffness that ensures that all the components remain in contact when the cam operates at a specific RPM. Now let's go to the next page and open up the model. Now before running a motion analysis, you will need to ensure that all the components in the assembly have mates defined that control their movement. Now these mates are sometimes referred to as joints. Now you can move around the various components to make sure that the appropriate joints or mates have been defined to control their motion. Of course, none of these components are in contact, which is something that can be defined during the setup. Now here's a handy tip. If you'd like to restore your assembly to its initial configuration, you can do so from the File menu. Now select the Reload button and hit OK on the dialog box that pops up. Alright, the component positions have been reset. Now it's time to set up a motion study. Typically, the third tab at the bottom is the Motion Study tab. In this exercise, it has been renamed to 1200 because of the 1200 RPM we're going to apply to the cam. Now select this tab and you will see the motion analysis has already been set up. Now by default, SOLIDWORKS has an animation and a basic motion tool that lets you animate your assemblies. But if you're attempting to simulate contacts and springs, it is recommended to use the full-blown motion module. Now this can be added from the SOLIDWORKS Add-ins tab on the Command Manager. Now select the SOLIDWORKS Motion button and you will notice an additional button on the Analysis Manager. Although the analysis is already set up, let's start from scratch so we can walk through some of the nuances of the setup. Now this can be done by right-clicking the Motion Study tab, in our case the tab named 1200, and selecting the Create New Motion Study. Now make sure you have the motion analysis type selected. Now any change you make to the orientation of the assembly is recorded. Now this can be a little counterproductive if you need to investigate the assembly while it is in motion. So to avoid this, right-click the Orientation and Camera Views item and select the Disable Playback of View keys. Alright, everything you need to set up the analysis such as motors, springs, dampers, contacts, and gravity is in this area. Let's start off by defining the spring between the valve guide and the valve. Now you can make edge or face selections. Just ensure that these selections are concentric or have common centers and are between two different components. Here I have the valve face and the guide edge selected. Now I'm going to start with a soft spring. So let's set the spring stiffness value to 0.1 Newton per millimeter. Next, the free length of the spring affects the preload. The free length is always automatically determined by the software based on your selections. Any value higher than this will introduce a spring preload. So let's set this value to about 60 millimeters. Now everything under the display section just controls what the spring looks like and does not affect the physics. Here, the default values look pretty enough, so we'll just leave it at that. Next, we will apply contacts between the various entities. Select the contact button and ensure the solid bodies button is selected. Select the rocker and the valve. Now this will automatically generate one contact pair. Now the materials section controls the contact stiffness and friction. You can either input these values manually or select a set of materials that are similar to your design. Let's choose steel dry and steel greasy. Now repeat the same process for the rocker and the cam. We will use the same set of materials to define the contact stiffness and friction coefficient. The last step in the setup process is to add the motor that drives the cam, so select the motor button. In the motor definition section, you will need to select a circular edge or a cylindrical surface to define the motor axis and direction. You can use a double arrow to flip the direction so the cam rotates clockwise. Now let's set the speed to about 1200 RPM. Now you can control the duration of the analysis by changing the second black marker on the timeline. Here I'm going to right click it and set it to 0.1 seconds. Spinning at about 1200 RPM, this should give us about 20 revolutions in 1 second and 2 revolutions in 0.1 seconds, which should give us enough information to evaluate the mechanism. You can reset the timeline scale by selecting the zoom to fit button on the bottom right hand corner of the screen. Finally, it is essential to visit the motion study properties to set the frame rate for the calculation. Hit the little gear icon and set the frame rate to 100 frames per second. Of course, since we have a very small time interval, it is recommended to set this number to a higher value, say 500 or 1000. Now I'm just trying to stay consistent with the tutorial, so I'm going to leave this at 100 for now. Now to run the analysis, select the calculate button. A warning box appears indicating that your frame rate value might be a little too small. We'll ignore this for now and hit no. This should start the calculation. Once the calculation is complete, you can play the animation for the mechanism. In our case, since the time interval is so small, we will have to reduce the playback speed. Let's set the playback type to normal and the speed to about 0.01x or about 0.05x. Yeah, that's much better. Now let's plot some results. We'll start by looking at the contact force between the rocker and the cam. Select the XY chart button. In the window that pops up on the left, let's set the category to force, the subcategory to contact force, and then grab the resultant or magnitude. Now select the two contact faces from the graphics window and hit the green check mark. Now the resulting graph shows you that the contact between the two surfaces during operation is continuous and has an average force magnitude of about 1 pound. Of course, the plot is jagged because of the frame rate, but this can be improved by setting a much higher frame rate prior to the calculation in the motion analysis properties. Now let's increase the speed of the cam to about 2000 RPM and rerun the analysis. Now you need to ensure that before making any changes, the timeline slider is set all the way to 0 seconds. Otherwise, the analysis tool will record any change you make to any item at a specific time instance. We wouldn't want that. We want all the changes to be made at 0 seconds. Alright, let's modify the rotary motor and change the RPM now that we've reset the slider. Hit the calculate button again to run the analysis. Once this is done, expand the results item from the analysis tree and investigate the contact force. All the plots that you have saved will show up under this item. So right click plot 1 and select show plot. The contact plot is again jagged because of the low frame rate, but the information presented is still valuable. Now the plot shows that at 3 points the contact force will go to 0, indicating that the rocker and the cam potentially separate at these points. Now this can be corrected by increasing the spring stiffness. Now let's right click the linear spring 2 item and hit edit feature. Now change the K value to 10 newtons per millimeter. Rerun the analysis and check the contact force plot again. You will notice that the force has increased significantly to about 60 pounds, and there's absolutely no chance of separation between the cam and the follower at this RPM. The higher force can obviously be attributed to the increase in stiffness and hence the preload on the spring. Finally, a common output that users expect from the motor actuated mechanism is motor torque. This can be done from the XY plot menu. Set the category to forces, set the subcategory to motor torque, set the resultant component to either magnitude or pick a direction, in our case it's Z. Finally, in the blue definition box, select the rotary motor item from the analysis tree. This should display the motor torque versus time. While this is the component plot, here is what the magnitude plot looks like. Now through this exercise, we've used the motion analysis tool to simulate the valve cam mechanism to determine spring characteristics, contact forces, and motor torques. Some parting thoughts. Now the best way to gain confidence in the stress results to justify the safety of your components is to apply localized mesh refinements in areas that you doubt the results for. To help visualize this, let's overlay the mesh on this bracket model. You can do so by right-clicking the active stress result, selecting Edit Definition, and the Settings tab. Once in the Settings tab, change the boundary option from Model to Mesh and hit the green check mark. From the stress results, you will notice that you have a high stress area at the corner of the bracket. Now to get a better picture of what's going on here, you can increase the density of the mesh at this area and see if that changes the results. Now this can be done by right-clicking the mesh item and selecting the Apply Mesh Control button. Let's select the edges of the bracket with the high stress and the holes as well. You can then adjust the size of the elements that will be applied to these features. Let's set it to 2.5 millimeters for start. Any number lower than the global size should work for now. Now we will have to update the mesh with the new settings. So let's remesh the model, ensure we have the original curvature-based measure settings. You will notice the change in the element size closer to the features that we previously selected. Now let's run the analysis. Once the run is complete, investigate the stresses. You will notice that the stresses are higher than what we saw in the previous run, but is concentrated at a smaller area. The stresses around this concentration point are similar to the previous results of about 210 megapascals. Now this is very typical behavior at these sharp corners and can be considered to not drastically affect the strength of the design. Now this can be verified by running another round of mesh refinement at these localized points. Expand the mesh control item and edit the definition for control 1. Now let's reduce the element size to 0.5 millimeters. As always, we will need to update the mesh. Again, pay attention to the increased mesh density in the local areas. Finally, let's run the analysis. Once the run is complete, you will again notice the stress values rise, but is concentrated at the point where the three edges meet. Now, unless the component is being fatigued or is susceptible to corrosion around this area, the design can be regarded safe. Once again, the stresses around the concentration point still remain to be around 210 megapascals, like our previous two attempts. Alright, so I hope you found those instructions useful. We took a look at how we can run a simple structural analysis of a part, a structural analysis of an assembly, and how we can monitor structural performance of your design as you're making small changes to it. Finally, we also took a look at how we can run a simple dynamic analysis on a mechanism with our motion analysis tool. We did all this within our SOLIDWORKS CAD environment too. Now, if you really like this video and you'd like to see similar tutorials to help you get ramped up with SOLIDWORKS or simulation, we have an online knowledge base called kb.goengineer.com that has many similar tutorials. Again, this is Arun Thiraviam. I hope you found these instructions useful. Thank you and have a great day.